the first architecture that showed the advantage of a convolution-based neural network. We added a few modern flavor using batch norm, and we achieved a very good performance on fashion MNIST. But the problem is still, this is a large model compared to its depth and its limitation. It uses only one filter size, 5 by 5. But here in this session, we will talk about ways to capitalize on this performance while making it simpler and develop heuristics for better designs. Just a footnote that after LeanNet, AlexNet came, and it did increase the depth and added different filter sizes with a very similar architecture. Though back in that time, they had to chop the model in two to manage the GPU aspects. We don't have that problem now. And basically, if you look at LeanNet, AlexNet is a deeper version of this with an additional 3x3 convolution in the next sliders. Okay, so let's ask these questions first. Why we are using 5x5 kernels in LeanNet? Can we use a smaller filter? So smaller filter means less parameters, right? And how can we increase the depth of the network without the vanishing gradient? And then looking at the parameters usage in the model. Where is the bottleneck? Where are the most parameters? How can we reduce them? And then how to make our life easier? Coming up with blocks in this design. So a block is a combination of layers that can be repeated, and we know that that block is highly optimized. And if we stack them in an organized way, we can achieve a good performance while having a bird eye on the design without getting lost in things that we already improved. I mean, we don't want to redesign them. So to answer these questions, we are going to go through a few architectures. We start from VGG, and then we build on top on that, and then we get to changes that lead to other architectures. Okay, so let's start with VGG. VGG tried to answer the first question. They basically show that 3x3 convolutions, when stacked on top of each other, can give us the same receptive field as bigger size convolutions with less parameters. So, for example, here, a stack of 3x3, a two-layer 3x3, not only gives us the same receptive field as one 5x5 with less parameters, it also infuses more nonlinearity than this with one layer. So notice that we will have one injection of nonlinearity here and one here via the activation functions. So if the number of channels in and out is the same, the 3x3 number of parameter, the 3x3 gives us 18 multiplied by channel squared versus 25 in the 5x5 case. So in fact, if we add another layer of 3x3, then we will have almost the same parameters, 5x5, with more receptive field and much more nonlinearity. So the idea was, let's make a block with this stack of 3x3s with padding and max pooling for our convolution parts of the network, and then just stack them on top of each other. So let's compare this idea with the AlexNet that we discussed in the previous slide. So here, first look at the AlexNet. So like I said, AlexNet is an architecture that is very similar to LeanNet. It has more convolution with different filter sizes. So recall that LeanNet was on the MNIST data, but here AlexNet was developed for ImageNet competition. And back then, it smoked the competition really with a large margin. However, this is, like I said, a very, very large network with many parameters. And of course, this stack of different convolution, so note that the convolution layers are in blue here with their max pools, needs to have a lot of ablation and good design to make these choices. What VGG is offering here is, I'll give you a block. You don't need to really do a lot of work here because this is highly optimized. We showed that this can do more impact than the alternatives with larger convolution filters. So note that 3x3 is the smallest convolution unit. So we are looking at the smallest convolution unit, a group of them with good padding and max pooling. And once you have this block, just stack them on top of each other and give it to your classification head. So why this is very significant in design? Because of its ease of implementation. We basically repeat the same structure in a for loop and give it to our forward. So with that, let's go ahead and implement this. We are going to implement the block and show some aspects of it. Okay, with that, we are going back to our code, still fashion MNIST, loaders, and the train one epoch, evaluate. We still have the advanced MLP, which I removed because we don't need it anymore. But we are going to use some of these helper functions. Okay, so before going forward, let me just write a function that counts the parameters of the model. This will be useful when we are trying to discuss the changes in the model architectures. So now we want to make a VGG block. So if you remember, a VGG block is a stack of 3x3 convolutions with of course, max pooling. But in each one of these 3x3s, we have a batch norm and a ReLU. So maybe even before making the block of VGG, we can make a block of 3x3 convolution batch norm ReLU, right? That's the smallest component, the atom that we will build other blocks with, right? So first, let's build this, and then build the VGG block, and then we can go toward the VGG network. So with that, gonna write a convolution batch norm ReLU. And here I see that the suggestion is to go with default, which we can, of course. But here, since we don't want to redo something, we already know that, let's just try something else. Well, this is absolutely okay. You can, of course, do that. But here, for the sake of trying to be more savvy with this block design, let's just go with a more abstract design. So I'm going to directly ask for sequential and takes the channel in, channel out, kernel 3, padding 1, stride 1, and here we have bias false. So bias is false because we are not going to need bias. The batch norm already has a bias within it, so we really don't need. And we can actually even consider this in a lower level when we are building the convolution itself. So just consider, remember that. And here, as you can see, this is also a suggestion, meaning that I could directly list the modules that I want that this sequential needs together. And if I do this, I really don't need a forward method because it does it by itself. So this is just a clean, to make it even maybe more minimal. I'm gonna just change this notation. I'm going to send this to a lower level because I do want to control it. Less is more, always. And I'm going to make the ReLU in place to save some memory. Okay, so that's our convolution block. And I'm going to use that to make our VGG block. Okay, so, and my VGG block, let's just go default with this. So this is the number of convolutions we want within the block. And for I in number of convolutions, of course, the range of that, I want to append these layers, right? So maybe we should initiate this earlier. I'm gonna just make it empty, but you saw the suggestion and the reason more clear here. We want the first layer to have its own channel input to be independent from the others, as we can use this block anywhere. So the in channels for each one of these layers that I'm going to append will be Cin if it's the first layer, and it will be Cout if it's the intermediate layers. Okay, so that's the reason. And we are going to append them all together. So note that I could do the NN sequential again here. And if I did that, I was not forced to write a forward method. I didn't do it, so you can do it yourself or maybe practice, but here I have to write my forward. Okay, so here, just maybe a design point. I'd really like to separate my convolution stack from my max pooling stack. And this way I will be able to, for example, maybe I may want to change my pooling to average, or I want to have a choice later to do some ablation. So to do that, let's just change the appending strategy and separate the pooling here. And let's call this conus, and then we have the pool separate. So in that case, we now have to change this. Okay, now let's test for an input image of 2 channel maybe one channel, just like fashion eminist grayscale. And let's say we have two images in a batch. What happens if we send that through this VGG block that has two convolution? Of course, we can increase that if we want. And let's say that we are asking for 32 different features. So 32 channels in the output. So if we do that, what will be the size of the output? So basically, if I have an image, let's just make a random torch and then send it to the VGG block. I'm asking what's the shape of Y. So pause the video, think about this. So the output will be 14 by 14, and there is this, of course, the pooling. So now that we have this, we're good to go. We can write our first VGG neural network. So to do that, let's just call it a VGG simpler. Let's go just with two VGG blocks and then a simple classification. It should be easy. So def init. Let's specify the number of classes. Convolution layers basically split out the features for our classification layer. It's a sequential of one VGG block, 132, two convolution, and another one with the input channel of 32. That is the output of the previous one, and 64. Okay, so the output of this one will be a 7 by 7. Okay, let's just make it even smaller because it's supposed to be simple. So let's just show that we have control over these VGG blocks. Okay, that's it. That's the convolution stack. Let's make the classifier sequential. That flattens the input, destroys all of the spatial information, but we don't care because we are giving features. It's already encoded with our convolution. Okay, it takes in the input, and this will blow out to be very a lot of parameters. Let's just simplify this. 128, 128. Done with the classifier. Then let's write a forward. Now let's just check the number of parameters, and we have 500,000 parameters here. This is still a lot, so we have to do something about this. Let's go back to our quest here. So we reduced the number of parameters in our convolution stack compared to the previous architectures, LeanNet or AlexNet. But if we look closely, in our stack, we always increase the number of channels. So this is like increasing the number of features, aka the number of dimensions. So even if we reduce the height and width, if this reduction is not with the same speed, eventually this will blow up. And at the end, we are still dealing with this dimensionality problem. Channels is basically the determining reason for the number of flops too. If you increase the channel from 1 to 2 or anything beyond 1, it's now you're dealing with a multi-dimensional cube that you're doing a convolution over it. So that's why it's the bottleneck of our computation. So we really want to control these channels. So we are going to talk about an idea that we haven't yet thought about, and it's basically pulling across the channel. And to do that, we will introduce this one-by-one convolutions. So let's start with this. So the idea is rather simple. For example, if you had only one channel, you look at just that feature for each pixel, and you basically multiply it by and the scalar. Doesn't do anything, right? But what if you have more than one channel? In that case, you can pull across that channels for that pixel. So everything is for one pixel. There's no spatial mixing. And then for that one pixel, we look at these features, corresponding features in that channel, and we come up with a linear weighting with a bias. And remember, this is basically the linear regression. So we make a linear regression over the values of the channels corresponding to that pixel, and we report the output. So this output can be one-dimensional or more, and that's the new channel for us. If you add a nonlinearity or an activation to this, you basically have your perceptron. So that's why this is a mini MLP. For each pixel, we make a mini MLP and we output new channels like this. This channel can be one or more, but usually this is less than the number of initial channels. Of course, it can be more, but usually it's less. And that's how we shrink the channels while not losing any information without processing. We are not dropping any information. We're just summarizing it with our tools, which here is a linear regression plus an unlinearity. And notice that we also inject some nonlinearity here. We always, in our design, this is the principle, always we inject as much as possible nonlinearity to increase the capacity of our networks. So hence there are names for the same technique. We have different names for it: feature map, pooling, cross-channel, parametric pooling, and so many other names for it. But if you remember, most of the parameters that we had in all of the designs so far are actually living in the classification head. So if we go back, comparing the classification head number of parameters to the rest of the network, for example, in this case, probably 80% or maybe 90% of the parameters are in the classification head. And we know why. Basically, in each convolution stack, the number of parameters is the number of values in the filter. We have one small network that we do the convolution. It's very small, but compared to this fully connected MLPs, they are not really the bottleneck. So we have to find a way to reduce this. This is where we can do the most damage to the number of parameters. And this technique here let us do that. Once we mix the information in the channels, we can use it to directly summarize and send to the classification result. So the idea is the output of this one by ones, which will be a bunch of features. Like I said, these are the output, which is a mixture of the features that the convolution finds. We don't need to really do the mixing again in a fully connected neural network. Let's just directly give it to a pooling, for example, averaging, and aggregate all of this information together. So what we achieved here, we achieved a lot of nonlinearity with not many parameters through this one by one layers, and we decrease the classification head size significantly. Okay, with that, let's go on and do the implementation of this one by one convolutions. And just a note on the name, network in network, it's because of this MLPs that are living across the channels. So we are going to keep the same naming. So class name block takes inherit all module, and then what we need inside this, we don't need the kernel size because it's always one by one. We just need channel input and channel output. Since we can have multiple of them, of these NIN blocks, convolutions within one NIN block. So I'm going to specify the different channel that we can have, different channel size in the intermediate one by ones. Okay, so let's just think about 3 different channel size, simplify for another. Let's actually add spatial mixing at the first count of P on ReLU. So then padding 1, now we can do the mixing of the channels. This will be convolution, but when we say kernel 1, and this is the next one by one, and we need another ReLU. Okay, so let's check this out. We forgot a comma here. So what we expect here, we expect that since we are not messing up the image size in this count of BN ReLU, and the rest is basically per pixel, there's no spatial changing. So the output will be the same spatial, and we can control the channels with whatever channel size that we want to be in the middle or output. Remember, the initial one is just the raw input channel. Okay, so let's make the network. So names, simpler, NN module takes in the number of classes. It's a sequential of an NN block. Then we do a max pool over this. Then another NN block. Let's just make it simpler. And then another max pool. Okay, so then we need a classification head, which is implemented by NN adaptive average pooling. We could do average pooling without adaptive, but basically we have to take care of all of these heights and weights, and even maybe in different batches. Here, adaptive, it bins the heights and weights in a way that average the value of the channel in those bins and output that and send it to the classifier. And the classifier is basically a linear regression, fully connected classification. That be a linear regression takes in 64 pictures, gives out the logit values for each classes. Now the forward. That's it. Let's count the number of parameters here. Okay, there's an error here. Oh, I see. But got 32, got 64. Okay. So let's compare the number of parameters between the NIN simpler and the VGG. And as you see here, we're looking at 500,000 compared to 30,000. That's a huge difference. Okay, so to do the training here, I repeated the code from before, the auxiliary code that we wrote for the loaders and training. And recall that we use the transform to tensor for both training and validation data when we are feeding to the model. Here I want to use this movement to add another concept that basically is called data augmentation. So the idea is for image data, we have this convolutional neural network that gives a translation equivalence for us. But we want the model to be able to do the detection for an image that is taken night or during the day. So these two images have different lighting condition, different color pads, and we want the model to be invariant to them too. So in those cases, what we can do is to just feed the model with images in those conditions, and because the labeling are the same, we expect the model to become robust against those variations. So here we can look at horizontal flip. For example, if you have a cat and you flip the image, it is still a cat. And you can also add some probability that in every 10 image, flip one of them when you're feeding to the model. The common one, like for example, we can do random rotation, for example. We can do cropping, random crop, random align. They all give the same. But it's important to remember we only augment the data during training, not during validation. And sometimes when we use pre-trained model, we should be more strategic in the way that we are doing this augmentation. For example, too strong transformation, if you change the angle for example, for building, it may break the class identity. So it's important to know how strong should be this augmentation. Sometimes it doesn't really help a lot in feature learning because we have a very strong pre-trained model that already does a great job in feature learning. We only need to change the classification. So we may not need this augmentation. So like I said, it is important to decide where to use it. Okay. So with that, let's do the training. Okay, there is an error. Let's see what's going on. In place operation, something is wrong with our RELUs. Let's go back. Oh, I see. We have RELU already in our convolution beyond RELU, so we don't need this. That's not the case in VGG. Okay, great. So this should do it. So I see the results are back. Let's just look at the validation accuracy here. And the VGG is going up. And we already broke the 90% with just a few epochs. And we see a respectable performance for the networking network, almost as good as LeNet. And remember, compare the number of parameters. We're achieving that with much less parameters. Took care of two situations. One was the blow up of the dimension with this 1x1s. The other one was taking care of this many parameters in the fully connected classification head. And then we came up with these blocks that can do optimal performance while help us doing our designs. So the next important modification is how can we achieve deeper architecture? That's where the idea of inception nets comes in. So back then we still didn't have ResNet, a way to go deeper without gradient vanishing. But now that we have this one-by-one convolution, it basically took care of blockers for us to go with more layers. We took care of the blow up. Now we can stack more layers. We know how to deal with heights and weights, with padding and pooling, and we now can control the number of channels with this one by ones. And now with that, we will talk about this new architecture, and don't worry, we will zoom in into these blocks. But the idea here is we can stack many convolution and this inception blocks because of all of this advancement that we had so far. So this is developed by Google. There is a Leanit reference here for respect. But the idea is here, now that we can budget the parameters, we can go deeper. And the other idea is we can also keep different scales in our convolution. Maybe if we look at different spatial scale at once, we may find better features. So when we zoom in into the inception block, firstly, we have this one by ones that manage the shape, mix the channels, prevents explosion of the dimensionality, and then feed that to these two different kernel sizes. And they are looking at the image simultaneously, spit out the found features, and we concatenate all of these found features. So note that we have the one by ones that, if you think about it, it's like residual really. It doesn't do any convolution after that. And then we have another channel here, basically pulls the information and gives to a one by one. All of these branches have their own nonlinearity injected. And here, the principles that we achieve is, first of all, we are not committed to a single scale. We are using different kernels. The height and width will be preserved. Of course, we will have many channels because we concatenate all of this. The pooling channel here is also gives a shortcut about the context. For example, if it's an average, like the average context, or if it's max, the most dominant concepts that can talk to the other features later. This way we solve this cost of going deeper to some extent. There's a lot of parallel computation, of course. We inject a lot of nonlinearity with not a lot of parameters, so cheap nonlinearity. Still factor as kernel, smaller kernels stacking together. And long story short, this was not enough even after all of this. And that's where residual connections came in and resolved the depth problem. Okay, so to recap about ResNet, if you remember, we just add a skip connection and learn only the fx here plus an x that we don't need to learn. Just a recap on what we can achieve with these baselines. For example, Leanit had about 60K, about 45K of it was in the classification head. We achieved 89% validation accuracy, but of course this is a large network. Then we discussed VGG, which about the same number of parameters, but of course with more depth, and it gives us, I would argue, more than 90%, and we just showed it in our code here. Even with 7 epochs, we can go even higher. And then the networking network, again, here we see that it's going up. Of course, if we continue the epochs, we may get even better performance. And we are getting close to Leanit with much less parameters. And then if we go for ResNets, again, deeper architectures, you can hit even more and more validation accuracy. And we will see that in the assignment. Okay, so like I said, the idea is let's use all of this, go for an architecture that is even smaller, but with a respectable performance. And the idea is we want to put this model on a phone, for example, on an edge device. And we know there are some limitations, for example, this much memory that we can use. So the model cannot be larger than this many parameters. So we want to be able to do our best with that given constraint. We want to engineer the model using all of these tips and tricks and principles that we learned. So we should know what are the extremes that we can go and then play within these extremes. So that's where the mobile nets come in. Like I said, these networks were designed for mobile or edge devices where we have this constraint of very small RAM, tight latency, and the budgets on the energy, battery power. So we have to reduce the number of parameters a lot without killing really the accuracy. We still want the spatial inductive bias, so we still need convolution. Let's go from this standard convolution where we do KK convolution. And instead of doing this, let's look at each channel, each input channel. For example, in the case of RGB, look at R, G, and B separately and do KK on each one of these filter. By KK, I mean KK convolution. And then mix the channels separately for each pixel. That's the NIN style, basically 1-1 convolution. So this way we split the spatial compute from the channel mixing, and this will reduce the number of parameters significantly. For example, in the case of standard one here, we have this many parameters, but if we separate them, we basically break the C out outside of this. We are looking at about 10 times fewer parameters in a small block. And when you stack them, we're talking about exponentially less parameters. So like I said, we will explore these ideas in the assignment. So with all of these advances and all of this data, the image data that we have out there, some of these models achieve very good performance. And we know that most of the features that we can find in images are shared across different objects. The idea is, well, why should we retrain these convolution stacks, or at least the early layers of it, well, when they are doing the same thing? So why don't we just go ahead and train a very good design stack of convolution layers and then use it for our classification purposes? Maybe we just train the classification head. So this idea is transfer learning, and it means that we can copy a trained model, freeze it. We are not allowing any backpropagation through its weight, and we only backprop through our linear layers. We can generate a very large data set, for example, ImageNet, that has about 14 million images and 1,000 classes, which requires a lot of time and compute to train a model on this. But if we already have a model that has the weights trained for us, that can work as a prior for us. So we will keep this prior and use it in our pipeline. And if we have more data, we will train more. We'll go back and train. So for example, if we only train the head of this network, the classifier, we call this a linear probe. We basically use the feature extraction and we linear probe. If we want to train more, we want to go back more, we call it fine tuning. For example, if we use a model that is trained on ImageNet with only a few epoch, we can achieve a 93% performance on FashionMNIST data. And we can, if we use more data from FashionMNIST, we can even fine tune the last block and achieve 94%. But we'll see that in the assignment. Okay, so let's do a transfer learning and a ResNet architecture that is available from Torch Vision. So we will use the ResNet 18 architecture. So 18 comes from the 18 layer of the network. And you see that there are two different blocks here. If you look up at figure 863, the first block has this basic block that is very similar to what we wrote. Conv, a 3x3, a batch norm, relu, conv, batch norm, and relu here is not present, it's off skip, and then relu. So that's the difference from the previous block that we wrote. Okay, back here. So we are going to use this. There is M here that we are not touching. Most of these layers will not be touched during the transfer learning. We are going to do linear probe for FC, and if we want to do fine tuning, we may include one of this last convolutional layer. Okay, so with that, let's go to the code. Okay, so you see that in Torch Vision models, I'm importing ResNet 18 model and its weights. Note that here in the augmentation, I put some transfers to make sure the ResNet 18 works with our fashion MNIST data, because remember that the ResNet 18 is trained on ImageNet. Okay, with that, the rest is basically like before, and we are going to the model. So for now, we are freezing the entire ResNet 18 and weights, so we are not activate gradient on that. So if we have freeze all, it means that we are just linear probing, so all of the parameters will be frozen. So model here is ResNet 18 trunk, and here for the FC part, we release the gradient, and basically we allow gradient. If we want to fine tune, so if we have enough data to go and deeper and train the last convolution layer, the layer 4, we can do this. So we allow a function here. So for linear probe, like I said, we are just training the FC, and for fine tune, we also train the last layer. The important thing here is we have different learning rate for the backbone and the head. When we are doing fine tuning, we allow larger learning rate for the classification head, and very conservative learning rate for the fourth layer of the convolution. And that's it. We can do the training and test this out. So this takes some time, but since you guys have a similar version of it in the assignment, I'm gonna stop here.